Welcome to exact equations. So first up, what is an exact equation? So a first order differential equation is considered to be exact if it can be written in the form partial with respect to x of capital X, f, evaluated at xy, plus the partial with respect to y of xy, or of capital function f, evaluated at xy, times dy dx, or times y prime, is equal to 0. We will often see this written in the format with differentials instead. As we have two, well, actually we can see this. So the top format is essentially the product rule with respect to x for multivariable calculus. We could also do the product rule with respect to y. So we have the partial with respect to x of the function capital F times dx dy, plus the partial with respect to y of capital F evaluated at xy, and that's equal to 0, or using differentials, the partial with respect to x of capital F evaluated at xy times dx, plus the partial with respect to y of capital F evaluated at xy times dy is equal to 0. So these are alternative formats that you can see. You will usually actually see that last version when it comes to exact equations. So the question here is, why are exact equations useful? Well, note that if we take the first partial with respect to x of the capital function f, and then we add on the first partial with respect to y of the capital function f multiplied by dy dx, this is just that product rule we saw. So this is actually the derivative with respect to x of the function capital F of xy. So what we have here then is, since 0 is just the derivative of any constant, then it turns out that anything of the form f of xy equals c will satisfy the equation. So the differential equation or the exact equation. So this is sort of using that product rule. Exact equations just come directly from differentiating a multivariable equation with respect to x when that equation is set equal to c. So the trick here is, if we do see we have an exact equation, the trick will be identifying the original function f that the exact equation comes from.